So, today so we will look at the soundness and completeness of the resolution method, but before that let us just briefly recap what we have done earlier. So, one of the things we did was that actually this example is the best. So, we showed that you could actually derive logical consequences from resolution, and that is what. So, this was like a direct proof of this property of symmetry from reflexivity and Euclideanness. Yeah. Okay. So, this was a this is a direct proof which is which essentially the idea is that the resolvent should be a logical consequence of the two parent formulae from which it is derived. The second thing we did was that we did refutation, right. So what you could actually do is you could prove the symmetry by assuming the negation of symmetry and doing the clauses, and if you start with and then you could have several possible ways of just using resolution to derive an empty clause. So, and this was called a refutation. In general, of course, one of the early properties we saw about proof theory, if you look at resolution as a proof rule, you have to realize that the derivation of the empty clause, I mean in all the examples that we have done, we ended up with just the empty clause. But in general, it is possible that you have a whole lot of other clauses too in the set. Yeah. So one of our early theorems about formal theories said that if you could derive something from gamma, from a set gamma, and delta was a superset of gamma, then you can derive the same thing also from that, right. So in the case of resolution, what that means is that if you start with some larger set T of clauses, then beside the empty clause you will also have some of those clauses hanging around. But the fact that you have a set of clauses, in which one of the clauses is an empty clause, implies that you have essentially derived a contradiction, because the set of clauses intuitively represents a big conjunction of formulae, and the empty clause represents the formula false basically. Yeah. So you have to be able to make the empty clause a member of the set of clauses that you derived, and that is sufficient. As soon as you can do that, you have essentially done a refutation. Refutation means that you are essentially trying to refute some claim. Yeah. So that is why you take this negation, and that is it is equivalent to a proof by contradiction. So both logical consequences and refutations can be done through resolution. So so in fact what often happens is that resolution in general tends to be more deterministic if you use it as a refutation than as a logical consequence, because it has the same problems of trying to guide the proof towards the logical consequence that you want, which is something we did here somewhere. Yeah, I mean where so from transitivity and symmetry, you have to do you have to guide the proof in such a way that you take some appropriate most general unifier which unifies exactly the kinds of things that you want in order to get this conclusion. Yeah. Whereas if you did a refutation, then the proof is more deterministic. You can just take some whatever most general unifier you can find and just do a blind derivation, then continue to find a most general unifier just till you somehow get the empty clause. So that's in some sense a more deterministic process, and therefore more useful sometimes for theorem proving. Yeah. Okay. So now what we will do is we will do the more meta theoretic aspect. So I will try to do the soundness and part of the completeness. The rest of the completeness I will just put up as slides. So the most important theorem on completeness I will put up as a I will put up in the slides, so that then the next which you can study for yourself. But after the vacation, basically, then we'll worry about the completeness of the Hilbert system, which is still pending, and we'll worry about undecidability and maybe formal theories like number theory or axiomatic set theory. You know, we have to do some applications. So we'll start with soundness. Okay. So we have this resolution method with all these conditions. So whatever those conditions are, assuming those conditions hold, you derive sets of clauses after using unification algorithm, which gives you a most general unifier. That most general unifier is important for the purpose of completeness, but at the moment we are just dealing with soundness, right. So all that we are saying is that this Cij prime that was defined. So this Cij prime, which is defined here, is called a resolvent. This resolvent is a logical consequence of Ci and Cj, where Ci and Cj are the two clauses against which the resolution was done, right. Okay. So this is what we will set out to prove today. One corollary of this is that actually there is something you can state a theorem essentially for which this lemma is important, but essentially we could have rewritten this lemma as a full theorem which says that the S prime that you derive from S is a logical consequence. S prime is a logical consequence of S, yeah, where S is the set of clauses in which Ci and Cj are some member clauses, yeah, and Cij S prime is S minus S. So this denominator is S prime, yeah. So basically what we are saying is that resolution preserves logical consequence, preserves validity. So if S is valid, then S prime is also valid, yeah. So in fact it might be a good idea to treat this lemma as essentially saying that S prime is a logical consequence of S, though we will focus on only a single step of resolution, so that it's clearer, yeah. Okay, right. So we'll just assume that we have these things as given in that resolution rule. We have Ci is some Ci prime union some P of Si prime, where there are various different set vectors of terms Si prime, and then the Cj contains Cj prime union not P of Tj prime, where there are various kinds of Tj primes, vectors of tuples, all depending on the arity of P. Okay. From the examples, it is clear that Ci prime could have other occurrences of P. It could also have occurrences of not P with other terms, right. Similarly, Cj prime could have occurrences of P and could have occurrences of not P with other terms, yeah. All we are saying is that there is some unifiable subset of terms in Ci and Cj, such that the terms you select from Cj prime are complementary to the terms you select from Ci, yeah. And of course, they are free variables. Of course, they are all we standardize the variables apart. So all the free variables are distinctly named renamed. So, there are no, so the free variables of Ci and Cj are empty, and this set Psi prime and Ptj prime, this chosen set is a set of unifiable literals, which the unification algorithm gives us some, for which the unification algorithm gives us some substitution. Yeah. So, one thing is, so supposing, so we will do this proof of logical consequence. We need to show that C prime I j is a logical consequence of Ci and Cj. So, going straight by definition, let us just assume that there is some sigma algebra A, which is a model of Ci and Cj. Effectively, that means that it is a model of each of them. The universal closure, this should be, this is an OR of all the literals in Ci, and this is the OR of all the literals in Cj. Yeah. Okay, so it is individually, if it is a model of this, then it is a model of the conjunction universally closed, but of course they have distinct free variables. So, the universal closure can be distributed, redundant universally closed variables can be removed from the individual clauses, and therefore, the universal closure of this and the universal closure of this are both satisfied by A. Yeah, right. And since this is a universal closure, any substitution that you have is also satisfied by this A. This is, yeah. So, so A is a model of any substitution theta of OR of Ci and theta of OR of Cj. If further, if theta is a unifier of L, then essentially what we are saying is that this set L, our unification algorithm keeps collapsing the set, right. I mean, set of all distinct terms after unification till there is exactly one term left. So, if theta L is a unifier, then let us say it gives you a single term lambda, then when you do the substitution theta, essentially a lot of those terms get collapsed. So, what you actually have therefore is, now moreover this theta goes across to Ci, yeah, and here goes across to Cj, and the result of unification is that all those Psi primes which were chosen become a single term lambda. All those not P Tj primes that were chosen become a single term lambda bar, right. So, that is what happens here, right. So, you can push the substitution in, and essentially what I get is that A is a model of this disjunction, where all those Psi primes have all gotten collapsed because of the substitution theta into a single term lambda, and then the substitution is applied on the rest of the clause, yeah, Ci. Similarly, here all those terms not P Tj primes have all gotten collapsed into a lambda bar, and the theta is applied to the rest of the terms Cj prime. Yeah. Okay. Now, what we are essentially going to show is, so you take this theta Ci prime and theta Cj prime. So, basically let us assume that there are some literals, there is some set of literals kappa I prime and lambda j prime. So, there are k literals in theta Ci prime and L literals in theta Cj prime, and what do they represent? So, depending on the values of k and L, we actually have this kind of a case analysis. Now, I had to contract the table so that it fits in the screen, but I think you will be able to see most of what is there. So, when you have when k and L are both 0, then what it means is that your theta C I prime is empty and theta C j prime is also empty, which means what you have here is just lambda and lambda bar, which are a complementary pair and they derive the empty clause. So, this union, which is what your, this is your C prime I j, yeah. Though of course, notice that I have not actually taken theta to be the most general unifier. This lemma holds for any unifier actually, yeah, it does not matter, yeah. So, essentially this is like this union is your C prime I j, the resolvent, and you can see that this empty clause is actually derivable, is not just derivable from these two, but it is actually a logical consequence of lambda lambda bar. It is like an AND of lambda lambda bar, right. And in the other cases, so if you were to take the case when k is 0, which means that theta C I prime is empty and therefore, you have only lambda there, whereas L is non-zero, then what you will have is, so you essentially have lambda bar, or that entire clause represents an OR of literals, OR of all this, and lambda and lambda bar or all this essentially is logically implies lambda 1 or to lambda n L, yeah, right. And this is essentially these are validity preserving logical consequences, right. I mean, so validity is preserved almost exactly like, so I mean you have to think of it this way, they look propositional, but we know that all propositional validities also work for universally quantified first order formulae. So, they are, you have to, so these are actually universally quantified on their free variables, right, but validity is preserved over that only because of the universal quantifier, right. So, all these propositional logical consequences also work for universal closures of first order logic formulae and they preserve this validity. So, in this particular, in the case of when k is non-zero and L is 0, I still have lambda or kappa 1 or dot 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 or kappa k, but that or is equivalent to lambda bar arrow this, right. And here I have lambda bar. So, by modus ponens I actually have kappa 1 or dot 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 kappa k, yeah. And when both k and L are non-zero, I prefer to write it this way. So, again I have lambda or kappa 1 or kappa k, but that is logically equivalent to taking the negation of kappa 1 or dot 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 kappa k arrow lambda, and this is lambda bar or lambda 1 or lambda L, but then that is the same as lambda arrow this, and then we have the transitivity property of the arrow, right. So, which allows us to essentially claim this, right. So, this is logically valid and it remains logically valid even when it is universally closed, and therefore, it preserves logical validity, right. So, in each case what we actually have is that this set lambda union theta C I prime, lambda bar union theta C j prime, it has theta C I prime union theta C j prime as a logical consequence, and a universal closure does not change the logical consequence, and therefore, what it means is that your A, the model A that you started off as a model of C I and C j is a model of C prime I j, and therefore, it is a logical consequence because A was an arbitrarily chosen model. So, for all such models which for all models of C I and C j, you have shown that they are also models of C prime I j, and therefore, it's C prime I j is a logical consequence of C I and C j. Yeah. Okay. So, what this essentially says is, okay, so now in particular, if you derive the empty clause, then what you are saying is, if you derived an empty clause from C I and C j, then you are essentially saying that falsehood is a logical consequence of C I and C j, and so that the inverse holds. The falsehood of course has no models, therefore, the original parent would also not have any models, which is what we have in this corollary. Yeah? If the empty clause is derivable from a set S of clauses, then S is unsatisfiable. Okay? And this lemma can of course be written more generally as, if S prime is obtained from S by a single application of resolution, then S prime is a logical consequence of S, and therefore, repeated applications preserve logical consequence. Remember that now we have moved away from logical equivalence in two ways. One, if you look at arguments in general, the fact that we convert arguments into sets of using the Skolem conjunctive normal form means that we have moved away from logical equivalence and remained only in equisatisfiability of models. Yeah? And your resolution does not preserve logical equivalence, it preserves logical consequence. So, what it means is that you cannot apply even if it were feasible in other ways, you cannot actually go through the derivation backwards, but that is true of any proof system actually, right. It only preserves logical consequence. There is a way of looking at proof systems that if what a theorem gives you is only a logical consequence of your axioms, then there is a way of looking at it as information theoretically a theorem has no value. I mean, it does not provide any fresh information. Yeah? So, that is a different philosophy. Let us not get into that. So, we are looking at, so essentially, therefore, resolution also preserves logical validity. Yeah. So, if your original set was logically valid, then any resolvent will also be logically valid, and definitely it preserves logical consequence, and you take the contrapositive, and that essentially justifies refutation, very much like proofs of contradiction. Yeah. So, if the empty clause is derivable from a set S, then that the derived S prime does not have a model, and therefore, S does not have a model. Therefore, S must be unsatisfied. Yeah. Okay. Right. So, so I do not actually have any more slides, but we will go through a proof on this. So, what I will do now is I will justify essentially a completeness. So, if you look at this, this says, so look at this corollary. So, what we will do is we will just we will say that refutation itself is complete. Yeah. And what I mean by that is essentially this corollary is like the soundness for refutation. If I can derive an empty clause using resolution from a set S of clauses, then that original set S is unsatisfiable. And what I need to do is to show that if S is satisfiable, then the empty clause can be derived. Yeah. So, this is what is going to be our completeness theorem. Okay. However, at the moment what I am going to do is restrict this S to only ground clauses. Yeah. So, this is like a preliminary lemma for ground and it in some sense also justifies the resolution method for propositional logic, because so trivially it follows that propositional resolution is complete, yeah, for propositional logic. So, but let us go through this. So, the interesting thing here is, so I have to show this, assuming that S is a set of ground clauses. If it is unsatisfiable, then the empty clause can be derived, and we need to show that. So, let us proceed with this proof as follows. What I am going to do is, I am going to do this proof using some measure. Okay. So, I define hash S, yeah, as, so let S be the set of clauses C1 to Cn. Yeah. So, there are n clauses, and hash S consists of, hash S is a number, and this number is sigma Ci I equals 1 to n, yeah. I take the number of literals in each Ci. So, basically I take the cardinality of the set Ci and I add up all of them, and then from this I also subtract n. Yeah. Okay. This is my measure. Okay. I take this measure, and the proof then is by induction on hashes. Yeah. This measure has been chosen in such a way that essentially you can start an induction by from 0. Yeah. So, if you were to start your induction, so if hash S, so you take your basis, and if hash S is 0, then what this means is that this summation is equal to n, right. Now, this summation can be equal to n if and only if every clause is a singleton clause, right. So, this summation cannot be equal to n, so which means that the case when hash S is 0 means that every clause is a singleton, every clause contains a single literal. Yeah. If every clause contains a single literal, so essentially what we have is that your S represents the logical formula and of lambda I, where lambda I is the singleton, is a single literal representing clause Ci from I equals 1 to n, right. So, if S is this, and you start with the assumption that S is unsatisfiable, S has no models, then we had a theorem somewhere which showed that there should be a complementary pair, right? Where is that theorem? Was it in normal forms? Scolomization? Scolomization, I think, yeah? Herbrand's theorem, Herbrand trio of interpretations.
Before this.
Huh?
Before scolomization.
Before scolomization. I think, yeah, it was sometime after moving quantifiers, Prinix normal form, Prinix conjunctive, Herbrand algebra. Okay, here, this is the one, yeah. So, which means that there is a complementary pair. So, if there is a complementary pair, then of course you have derived the empty clause, yeah. So, the basis is trivial. So, let us take the induction step. So, the induction step, okay, so this implies that some lambda I is the same as some lambda j bar for some I and j, yeah. Okay. So, the induction step is when hash s is greater than 0. Okay. If hash s is greater than 0 and you have n clauses, that means there is at least one clause, one CI which is not a singleton. Yeah. Okay. So, let me assume that this CI, let me isolate one literal from it. So, let me say that this is, so it contains at least two literals, of which of course this di is not empty, yeah. Okay. Now, let us look at, so let us look at Si1. Si1 consists of S minus Ci union di. So, basically, okay, this is one thing, and let me consider Si2. Si2 consists of S minus Ci union this lambda I, yeah. So, we split one clause Ci into two parts, we separated out one literal from the rest of the clause, and now we are considering two sets where it is clear that hash Si1 is less than hash S and hash Si2 is less than hash S. Okay. Now, we have to do some reasoning. Okay. The claim is that if S does not have a model, then Si1 and Si2 do not have models either. Okay. Because from the soundness it follows that if Si1 has a model, then S would have a model, because what are you doing? This lambda I, you separated out that Ci with this lambda I. Essentially what you are saying is that this Ci is logically equivalent to an OR of the literals, right. So, if Si1 which does not have lambda I, if it does have a model, then ORing a lambda I there does not change the model, it does not make the model invalid. Yeah, the same model will hold, and in fact so the same argument holds. If this Si2 has a model, then by adding a few more literals in an OR there, you have not you are not destroying that model, the satisfiability of the model, right. So, which means that, so it follows that if S does not have a model, then Si1 and Si2 too do not have models. They have measures which are smaller than S, and if Si1 and Si2 do not have models, then from by the induction hypothesis it is possible to derive the empty clause from each of them. Yeah. So, that is the next conclusion. So, essentially what you are saying is that the empty clause, I am just going to use this, is derivable from each of Si1 and Si2. So, there are two resolution proof trees. Basically, you start with Si1 and you go through some sequence of resolutions, and you end up at one place where you have an empty clause and probably other things too, but the empty clause is the important thing. And you start from Si2, you go through your resolution proof, and it is possible to find an empty clause here, whatever else might be there. Yeah, but that does not prove a damn thing, right. Now, what I do is I look at this proof tree. This Si1 did not have lambda I, right. So, I look at this proof tree, and supposing, and I say supposing I had taken Si1 with the lambda I inserted there in Di, so that this thing again I restore Ci back, okay. Yeah. And then supposing I look at this proof tree, so which means I have essentially replaced this Si1 by S. The proof tree still is valid, except that there are two possibilities. One possibility is that this empty clause is still derivable. Okay. The other possibility is that instead of the empty clause being derivable, I do not have the empty clause, but I have this lambda I occurring as a singleton there, right. Those are the only two possibilities. If I consider this same proof tree, then this is what will happen. If I put back my lambda I into Di to restore Ci, then this is what can happen to this proof tree. Okay. Now, okay. Okay, let us look at SI2. Okay. Now, SI2 had lambda occurring in it, okay, lambda I occurring in it. I claim that if this empty clause here, if this one does not have lambda I occurring in it, then lambda I went as part of a resolution step somewhere, right. If lambda I went as part of some resolution step here, and that resolution step was never used here, then that resolution step can now be used here. Okay? Fine. If lambda I is, if lambda I continues to reside here, I mean in SI2 throughout this proof tree, then the proof of this empty clause is independent of lambda I anyway, and would be, can be incorporated here. So, which means that lambda I would not have occurred in this empty clause. Right. In either case, I can derive the empty clause from S. That's yeah. I hope that is convincing. Yeah. Is there any? There might be a sub case I have left out.
You said that that same resolution step will be applicable at the last step of if lambda, where we got the lambda out of SI2.
Ha ha ha.
Intuitively it is kind of clear, but how do you formally say, I mean, how do you formally claim that?
No.
Intuitively I can understand, okay, the same, the resolution step that we used in the resolution of SI2 should be.
No, we are not just doing a copy and paste of the resolution steps. We are doing something more complicated. All we are saying is, if you can track the exact occurrence of lambda I in this proof, there are two possibilities. Either lambda I went away as part of something. So, the some other clause had lambda I bar, okay, and lambda I and that lambda I bar were chosen literals for resolution and it went away. Okay. So, that means in this case there are two possibilities. Of course, remember that of course. So, so that means that if lambda I continue to remain here, then that lambda I bar step was never used. So, there is a lambda I bar hanging around here. So, now I can resolve those two and I can derive the empty step. Yeah. Now, if what was the other case?
When there is still a lambda in SI2.
If there is still a lambda I here, if this lambda I that was there continues to reside somewhere here, then anyway lambda I was not involved in the proof of the in the derivation of the empty clause. So, which means I can still derive the empty clause here, whether there is a lambda I or not. So, I could have derived that without it, and adding that lambda I would still get this empty clause, which means that this lambda I would not be in this set. In either case, therefore, I would have derived an empty clause from S.
So you said there will be lambda I bar still in the resolvent of.
No, I'm considering two separate cases.
In that case, you said that there will still be a lambda I bar in the resolvent of SI1. So my question is it not possible that the lambda I bar could have been used in some other resolution step of this proof?
Yeah, but then what I am saying is, if then what you are saying is you are using the fact that the resolution might involve more than one pair of literals, right? Because we are talking of subsets of literals of the same kind. That's all you are saying. Then all I am saying is, in this case also modify this proof so that this lambda I also goes as part of that proof, right? So that is not a problem at all. But in either case, I would have derived an empty clause from S, and therefore, for ground clauses at least, this step is complete. I mean, this resolution is complete. Yeah. So this is actually the most interesting lemma, because the other lemma, the main theorem which we need to show is that in the presence of free variables and blah 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 blah. Basically, what are you saying there now? We will do resolution there if I have, let us say, p of x and not p of y somewhere, then I will do this substitution x for y or y for x and maybe do this do the resolution, right. But that is essentially like saying, take all ground instances of p of x, take all ground instances of not p of y, and for every p of some term here, I can find a not p of the same term there, and I can do propositional resolution, except that that could be infinitary. The number of terms instances could be infinitary, and so we resolve p x with not p y, for example. Okay. So, the propositional resolution proof is actually the most interesting, because the rest of the thing is really a formalization that if I did it with variables, and then I can find various ways. The only other interesting aspect, which is different from the propositional resolution, is the fact that we are taking whole subset set of literals at a time. That needs to be justified. So, for that we require some extra machinery. So, there is a lemma called the lifting lemma, which I have to prove, and then I will prove completeness for the main theorem. But what I am saying is, I will create the slides and put them up, and I will leave it to you for as self study. Since on Friday we are having essentially an open session, yeah, which we do not want to record. Yeah. Okay. So, I will stop here now. Yeah. So this essentially should convince you that propositional resolution as a single rule of inference is complete, is sound and complete. Yeah. And so we will stop here.